and welcome to the R portion of a Bayesian approach to linear mixed models. My name is Eduardo Coronado, and I'm a data scientist soon to join a consulting firm, and I recently graduated from Duke University with a master's in statistics. So what I'll be covering in this coding section is how to implement and do a very limited evaluation, some diagnostics, on a Bayesian linear mixed effects model. I will cover more advanced diagnostics, model checking, and model evaluation in a subsequent article. So just to provide some context, this will focus on some simulated website bounce rate data, which I will show you in a second how that looks like. It has bounce time as being your response variable, age as your predictor, and county as the grouping variable. And the whole idea behind writing this article was to show how fitting a Bayesian model can be a little bit more approachable than people might think, thanks to libraries such as BRMS in R and PyMC3 in Python, which take a lot of the more technical backend fitting that sometimes is needed by knowing how to create a model in Stan, for example, to be able to run these models. And so my hope is that this makes implementing these models a little bit more straightforward for those who haven't had a formal training in Bayesian statistics. Okay, so now that we have the data, the first thing that I'll do is I will center scale our age variable, which you can very quickly do with dplyr. And as you can see, we have that new variable, and we can move now to the next step of the modeling process, which is doing a quick EDA. And I would like you to keep in mind that EDA shouldn't just be plotting data. You should think about it as an iterative tool that allows you to better understand what models might make sense to help explain the relationships within your data. So as a very simple approach, we might just want to fit a linear model. And we can do that with a geom smooth function in ggplot. This is basically what I'm doing in this with this commands. And as you can see on the right, I've colored each county with a unique color, but I've put like the population kind of like trend line, which we can see might have like a slope of about 4. Even I did check it by fitting an actual model, but we can see that it has a positive slope. However, if we see kind of like the different groups, we can see that maybe some of them might follow that trend, some might not. So we might be tempted to potentially, explore other models like a mixed effects model. And we can also use CDA in the same manner. Now we can use both a geom smooth such that it can fit the actual population line that we had before, and then we can use another geom smooth to then compare it to how it looks with each individual plot. So as you can see here, we have an example of Simpson's paradox in which the population, if we weren't to consider the grouping structure, we would be having a very different relationship between the bounce rates and the age variable, because some of the individual groups don't have as positive slope. However, what we can see also from doing this kind of EDA analysis is that there seems to be some variation in the intercepts. Some of them are down here, some are up here, and there might be some potential varying slopes. This one looks a little bit negative, this one looks positive, this one looks like maybe close to 0. So this kind of like gives us an idea of potential models that we might want to explore. But the whole point of the EDA is that it helps us build models from the ground up. in which we start with a very simple model and then iterate through to more complex models. And EDA is a very useful visual way of doing so. Okay, so if you're somewhat familiar with Bayesian modeling, you know that one of the big challenges of Bayesian or fitting a Bayesian model is picking good priors. And this is something that some people find more challenging than others and might feel like adverse to maybe try a Bayesian way because they don't want to like bias the results or they don't know how to choose these. So I'll guide you through a very useful way of doing it, and is basically simulating fake data using your set of priors. This is what is called the prior predictive checks, and basically it allows you to see whether your priors could generate plausible data sets within the range that makes sense, versus like just having impossible values based on some values that you choose in your priors. So as an example is, let's say you use a very generic weak prior, which puts a lot of weights on the tails. And maybe in some cases it might make sense. Maybe in this one it doesn't. And it gives us like simulated bounce rates of, I don't know, 10,000 seconds. That sounds like a kind of a implausible values for bounce rates based on the data that we're observing and based on like what we might think about how long can somebody really stay on a website. So that is kind of like how you should think about this. And you can create like a flip book or like multiple simulated sets to kind of see whether these priors that you chose make sense. Okay, so let's run with an actual example. So the model that I'm trying to exemplify here is a random intercept model. We have beta 0 fixed intercept, a beta 1 fixed slope for the standardized age variable. We have B0J, which is a random intercept which varies across counties, each county J. And we have sigma squared as being the population variance. And so we can set up a set of, a couple of priors for those fixed and the random effects. And so what I'll do here is I'll first set up, a couple of seeds such that every time we run this, it's the same. You can change that where you can leave it or not leave it, but I'm doing it just so it's reproducible. And what I'm doing here is I am using the rnorm function to sample the group-specific variance, which I'm calling tau, the population variance, which I'll call sigma. This is for each one of the observations. Then I'll use tau to then get random intercepts for each one of these counties. And I also sample the fixed intercept and fixed slope. And having all that information now, then I can get all my simulated data, which will be the same size of the actual data set. And then I'll store it in a data frame where I will have like a label, which is going to be the simulation number, the observed data, and then my simulations. So once I actually go ahead and run this, then I can actually use the ggAnimate library to render this. Basically what it does is it allows you to use one of the variables that you have in your data frame to use it as a way to transition across different data sets. It's quite intuitive and it builds upon ggplot, which makes it very powerful. And so as you can see on the right, these are some simulations that we just ran. And on the y-axis is the simulated values. On the x-axis is the actual observed values. And the main point that you should get out of this is on the y-axis, we don't see any implausible values. Yeah, some values will reach like 500, maybe 600 seconds, which is still plausible, but we never see like 1,000 or 10,000 value on the bounce rate. So that kind of gives you, a sense of kind of like security that your priors will be giving you probable values, but not implausible values. Okay, so now we go into fitting Bayesian models. So as I mentioned, we saw initially that potentially the there is we can use the very basic linear regression to make it like a baseline model, and then we might want to fit a couple of other models, mixed effects models, to kind of like see how they perform versus like this baseline model. And so what we can start with is we can start using the get prior. Now that we've run the priors, we can kind of like get a sense of how to fit the actual model and set up the priors in BRMS with a get prior function, which basically you can pass it a formula like you would in a general LMER or LM function, some data, and as a result, you see there's some priors specified by default for some of the different coefficients, which are labeled as class. If you have coefficients that have, let's say, right now we only have one covariate or random slope, but if you had multiple predictors, all of them would be class B, but the coefficient would change based on whatever the variable that you're using. So it gives you a lot of flexibility on how to set up the priors. That's one big advantage of BRMS. So now that we kind of like know kind of like how the structure is, we can set the priors using as a vector using the prior built-in function from BRMS and assign it to the class that we want. So here we're assigning one for the intercept, for the slope because we only have one predictor, and for the population variance. So once we do that, and we actually want to see how that looks like, as you can see, this is how we've assigned each one of these priors to the each one of the coefficients or the parameters in this sense. You can use any type of distributions that are available in Stan because BRMS runs on Stan. So that's another big advantage of BRMS. It is built in an intuitive with an intuitive syntax such that you can, if you're familiar with regular linear models or LMER, you can try to fit it with the same kind of like formula builder without having to learn how to build a Stan model and then pass it to Stan. So I've already run for your convenience the linear regression because it has to compile and it has to run everything. But the main idea is you have your formula, you have your data, you have a family you can specify. So this can even be a generalized linear model. You can specify some burn-in, so iterations to discard from like the Markov chains, set up the number of iterations, how many chains you want to run. You can set a seed, and then this control allows you to specify certain parameters. So the Hamiltonian Monte Carlo algorithm that BRMS and Stan run to do the inferences. I won't go into the details, but you can look more in the Stan website on how to use these controls. Okay, so I fit the linear regression, and I can go and like do your typical summary and just specify that. And as a result, I get a summary with some estimates for a simple linear regression, even for the population, and you get some credible intervals and some other performance statistics that you might want to look into. Okay, so now that we've done the simple linear regression, let's try a random intercept model. And as you can see, this is pretty much the same syntax as LMER. Now, what we see when we want to fit a mixed effects model is there are additional classes, such as standard deviation. And here we can, like, as you can see, you can specify not only the group, but you can also specify the coefficient. So imagine you had like random intercept, random slope, and you wanted a different prior for each. You can use those within your how you set up your priors as above to specify which prior should go with which parameter. So the only thing that we want to do here is since we only have an intercept, we want to just add that to our priors from the simple linear regression. And now, as you can see, I've just added that last normal. And again, I've ran, for your convenience, because it can take some time, the random intercept model. And it uses pretty much the same entries as the linear regression. And so it is pretty straightforward. Okay, and same as with a simple linear regression, we can get a summary as well. There's other functions that you can use to get the actual county level estimates and 95% credible intervals, but I'll let you go into that on your own. If you check the BRMS website, there's great examples. Here, the biggest difference is now it's telling us that the group level effects right now is just the intercept, and it has this variation, which we can think about it as this is like the within group variation across the or the group level variation for each of the counties. Okay, so now that we've actually fit two models, let's do some diagnostics, or very simple diagnostics. Again, just to reiterate, not covering model selection and model checking in this tutorial. This is just to see whether the Markov chains and the rest of the diagnostics that help us understand whether the whole algorithm was able to do correct inferences and it didn't run into any problems. So one thing you can do is you can use the Bayes plot library, which comes with very useful set of built-in functions. So first I'm gonna look at the divergence. So I'm gonna set a color scheme and I'll explain what divergence is. And I can use the MCMC part chord function to do this. And so if I plot that, it'll get, this is specifically for the random intercepts model. And what it does is it looks for divergent transitions. Very simply put, divergent transitions come from how the BRM, the underlying sampler that BRMS uses, which is a Hamilton in Monte Carlo, specifically the no U-turn sampler. And so what happens is sometimes you can imagine as the posterior as being a landscape, and the assumption is that it has to be fairly smooth. And so if for some reason there are parts that are non-smooth, the sampling is being done at the moment in a very energy efficient way, if you can think about it that way, and like in a gradient way using like first order gradients. And so if it hits a part that it's not very smooth, it'll kind of like diverge from this optimal path that it has like traced for itself. And it comes pretty much as a flag for you, in which it's telling you that potentially wherever it finds it, let's say if it finds it for most of the standard age fixed effects, you might want to be careful of making inferences with the samples from that parameter, because it's telling you that basically it didn't reach convergence, and you should maybe do some changes to how you parameterize your model such that it can efficiently explore that space and basically be able to get samples that give you higher confidence on the inference that you have. Sorry for the very long detour on that, but basically that's how you should think about divergence. If that were to happen in this model, the divergence would show up as green, neon green lines. But right now we're seeing all black, which gives us a sense of security that every single one of these transitions are non-divergent. Therefore, the samples from the posterior are from the steady state posterior. So we should feel confident of our inferences. We can also, if you want to do a bivariate plot, maybe not across all the different variables, you might want to choose two of them. You can use the parse flag, which the vars kind of like function works as like select and dplyr, so you can use like contains or starts with to select specific variables. So here I'm selecting sigma and something that contains Cheshire. And so here we can see that's the two, the bivariate plot. And here you could see potentially maybe divergent transitions still in green. If you see something that is like wrong, you might see them all clustered like in a neighborhood like down here or maybe down here. But if you see them like all around or behaving very similar to like the rest of the transitions, then those might be just false positives. And I talk a little bit about that in the article, so you might want to take a look at that. So we can also use the same base plot library to plot trace plots. And in the same way, you can select specific variables using the vars, and which has a dplyr-like selection mechanism. And so as you can see here, we have for each one of these, it's the two chains, and we can like explore if there's like good mixing. It seems that for these, there's good mixing. Let's see if I can like show you outside of our studio, kind of like how it looks like. It seems like it doesn't want to load, but the point is like you can use that to like check the trace plots. And as another traditional diagnostic, you also have an MCMC autocorrelation function plot where you can actually check whether there's a lot of autocorrelation between each of the different samples. Right now, you can specify what the lag is. Right now, I chose a lag 10. So as an example, here in all these plots, we see that the autocorrelation decays very, very quickly for this random intercepts. Maybe there's a little bit of, some type of autocorrelation, maybe on lag 1 or lag 2, which maybe a reparameterization of the model might help. But right now, it doesn't really bring, or raise any flags. So with that, this is basically a very bare bones introduction of things you can do with RMBRMS, and I encourage you to check out the Python version, the Python video for fitting these Bayesian linear mixed effects models. And I also encourage you to go and dive a little deeper in BRMS. It's a great package, and it makes it quite straightforward to fit Bayesian models, as long as you keep some of the fundamentals in check while you're fitting them. Thank you so much, and hope you've enjoyed this tutorial.